Now on to chapter 6 on chemical composition. So much sodium. The FDA recommends a certain amount of sodium in the bloodstream. Too much can cause high blood pressure and other issues. Uh, so FDA recommends that each person consumes less than 2.3 or 2,300 milligrams of sodium per day. This is the upper limit. Also, too little sodium can be also dangerous, but there's just so much salt and everything that, especially people that eat processed food, it's easy to surpass this. So, but of course, we think in terms of mass of sodium chloride. So, how can we figure out how much sodium per amount of sodium chloride in something? And that's what we'll talk about today. It teach you the skills on how to help solve this problem. So, and I've already mentioned this, that sodium chloride, they're different elements and they're in the same compound. But now what we're going to think about is the ratio between the masses in these compounds, and also use these information to solve problems. So other problems we can solve is how much iron is in a certain amount of iron ore. So if you are a chemical engineer at a plant and you want to figure out how much iron you can get from a certain amount of ore, and calculate how much you can expect from a certain amount of raw material. Same thing as if you want to figure out how much chlorine is in a certain chlorofluorocarbon. So like for instance Freon 12, and we will do a problem with this coming up. So first of all, let's talk about something else. And I remember, I guess I'm showing my age, if you played slots in Vegas, when you win, you'd spit out quarters and you collect the quarters, and then you can go and put them in the machines and that kind of thing. At the end, if you wanted to cash out and you have this big bucket full of quarters, you can just take it to the well, I don't know, cash out person, I don't want to say cashier, but the people would take it and then they would actually just weigh the quarters, and then they would give you the bill currency. So you can figure out how much, if you know how much each unit weighs, you can use checking out the mass or weight of something can tell you how much of that you have. So for instance, if you know that, so a customer buys 2.6 pounds of a certain size nails, and we know that a dozen of these nails weighs 0.15 pounds, how many nails does the customer buy? So you start off with the 2.6 pounds of nails, and we know that a dozen nails is the same as 1.15 pounds, and then the units, 12 nails per dozen, and then we're left with the total being 208 nails. So in this way, we're talking about something that's something we could actually feasibly count by hand, but eventually we're going to get to the idea that we're going to do this with atoms and molecules that we don't have the ability to count. Even so, counting 208 nails, I would not enjoy that job, right? So doing the weight is a lot easier. So we have a couple relationships here. We know that the certain mass of nails equals a certain number of nails. And we also know this sort of number term that we have a dozen is 12. So now instead of nails, we'll talk about atoms. And they're just too big. They're just too big and there's too many. So we need to have a way to count them in an efficient fashion. And so instead, we came up with a different number called the mole. And the mole is Avogadro's number. The mole is 6.02 times 10 to the 23rd. And that is Avogadro's number. And it's just like a dozen is 12. A mole is 6.022 times 10 to the 23rd. And it doesn't matter what you have. If you have that many, if you have Avogadro's number or something, you have a mole of whatever that is. And so let's talk about how this fits to other things. So about 22 copper pennies, and these are the pure copper pennies, not the copper-coated zinc that are more contemporary. That's about a mole of carbon atoms. 2 large helium balloons. This is about a mole of helium atoms. So and then that means they have 6.02 times 10 to the 23rd. I know it's 2, but I like to go to 3 sig figs. So Whereas is defined as 12 grams of carbon-12 is the definition of a mole. And we've got that, and then that's how we tell between mass and the number of atoms in Avogadro's number. And now, just like with the nail example before, we can count things by weighing them, and then we don't have to go and count them by hand, and especially with atoms that we don't have the ability to do that, besides the amount of time that it would take to count something that has 6 with 23 zeros after it. So let's do some conversions here. Convert 3.5 moles of helium to a number of helium atoms. So we know that this is one of the straight one here. 1 mole is Avogadro's number of helium atoms. So let's do the conversion. 3.5 moles of heliums times Avogadro's number of helium atoms divided by a mole, and then we get to 2 sig figs, 2.1 times 10 to the 24 helium atoms. So that's a lot of helium atoms, right? And that's from 3.5 moles. So let's do some other ones. Convert 1.1 times 10 to the 22nd silver atoms to moles of silver. So we're given the number of atoms, and to do this, we're going to have to divide by Avogadro's number then to get the number of moles. So looking at the units, and this is dimensional analysis. You have to look at the units. So starting with the number of silver atoms divided by what a mole of silver atoms is, we get 1.8 times 10 to the minus 2 moles of silver. So if you look here, we have a dozen large nails and a dozen small nails. They obviously have different masses. From this, different elements have different masses. So you can see here, sulfur, for instance, 32 grams of sulfur and is 1 mole of sulfur, and 12 grams of carbon is 1 mole of carbon. And you thought, wait a second, I thought that carbon was the basis for moles. Why isn't it exactly 12? Don't forget that there's the isotopic ratios. So these are carbon is about 1% carbon-13, and then a trace amount of carbon-14. And so the mass of carbon on average is slightly higher than 12. So all these numbers here, these are terrestrial weighted averages for the isotopic ratios, and that's where these numbers come from. So, but you can see here that a sulfur atom is going to be more massive than a carbon atom. As such, we need more matter to get a mole of sulfur than we need as a mole of carbon. And then the lowest, of course, is going to be hydrogen. A mole of hydrogen is only about 1 gram of hydrogen. So we've already mentioned the definition of AMU. Any element, it's the mole of one atom of that element. This middle point here, copper has an atomic mass of 63.55. That's not entirely true. There's only certain elements that have only one isotope. So aluminum, gold, and silicon are examples of those. Most of them have mixtures. So copper has a mixture. That's not a true statement. But 1 mole of copper atoms does have a mass of 63.55. 1 copper atom would have an average mass of that if we did a terrestrial average, but doesn't necessarily mean a single copper atom has that. And then the molar mass of copper is 63.55. So that from that, this is true that the molar mass here on Earth of copper is different areas could have different isotopic ratios, but I don't think. I think as far as this course is going to be run while I'm teaching, I think we're going to be mainly dealing with the planet Earth, other heavenly bodies, maybe perhaps, I don't know. We'll see. If this course is on this long that we'd have to change this, I will be quite impressed with both myself and my longevity and with the human race moving forward. So let's keep on going. And so we have these 4 elements here, 32 grams of sulfur, 12 grams of carbon, 7 grams of lithium. And it turns out they're all 1 mole of each element. And that also means they have the same number of atoms. And so for the lower the atomic number of the atom, the less mass that you need for 1 mole of that atom. So as you move to the left and to the upper part of the periodic table, it's going to be you're going to have the smaller numbers there for the moles. So let's look at some of these. Calculate the number of moles in carbon and 0.58 grams of diamond. And so we're given mass of carbon, and we will figure out the number of moles. And we get a mole is 12.01 grams. We get that from the periodic table. So if you look at the periodic table, it's that number there, the element number 6. It's going to say 6, C for carbon, and underneath that's going to say 12.01. That's the atomic mass of carbon. And then doing dimensional analysis, 0.58 grams divided by the molecular mass equals 4.8 times 10 to the minus 2 moles of carbon to 2 sig figs. And let's talk about another one. How many aluminum atoms are in an aluminum can with a mass of 16.2 grams? So given this information, and so we get the mass of aluminum. Hopefully now when you solve these problems, I want you to really start to think in terms of moles. When I solve these problems, I try to get into the moles as quickly as I can, and then from that do whatever conversion math that needs to be done, and then I can spit out whatever the answer is at the end that's asking for. So hopefully you're starting to think, first thing, I gotta find the number of moles. So we got mass of aluminum. We know we can get the moles of aluminum, and the moles of aluminum just Avogadro's number of that. So then we can just do that dimensional analysis. So I want you to be able to look at the periodic table and look at aluminum, and then look at the bottom number, and it's 26.98 grams of aluminum. And then start with the mass, 16.2 grams aluminum divided by the atomic mass of aluminum times Avogadro's number. And you can see the units cancel out, and you're given 3.62 times 10 to the 23rd aluminum atoms. So that there shows you using dimensional analysis can go and get that. And again, I usually go and think about the moles. That's the center of my thinking when I think about these problems and I solve these problems. So we can also count molecules by the gram, because now we've learned that mass is interchangeable. And with these, you can see we're going through a couple examples of these problems. And for you, though, you the student, you have to be able to take these ideas of dimensional analysis and be able to digest it, and then be able to solve these problems. There is no set formula that will work for every single problem. You're going to have to think your way through each and one of these problems. So there's not like this figure out, I can use this formula, and once I learn how to use a formula, it's all going to be easy. No, you have to learn how to generalize in the problem solving skills and solve this. So we can learn the material. And the other thing about chemistry is everything you learn in the previous chapters, you then apply to the future chapters. Sometimes we skip a couple chapters and it comes again to haunt you. So keep that in mind as you're studying. So let's look at then counting molecules by the gram. And also with compounds, we have formula units, and then we have ratios between the elements. And again, the idea, let's kind of have the moles be the center of our thinking. So, and we also know the molar mass and the formula mass. The molar mass is for each element. The formula mass is for the entire compound. So when you have the formula mass is for the entire compound, that's what's going to tell you how much of that in grams you need for a mole of that material. So for instance, calculate the mass in grams of 1.7 moles of water. So we have 1.7 moles of water, and then we can figure out the molecular weight of water. It's so 2 times hydrogen plus 1 of the atomic mass of oxygen, and from that you get 18.02 grams for water. And again, that's how you solve it. And now the solution for the whole problem, 1.75 moles of water, and then the ratio 18.02 grams of water per mole of water, to then get 31.5 grams of water. So now you can also, using moles, you can figure out mass. So you can go backwards, and you can do it for not just elements, but compounds as well. So let's convert between number of molecules and mass of a compound. So what is the mass of 4.78 times 10 to the 24 molecules of nitrogen dioxide? So we're given a number of molecules. Hopefully you're thinking, I want to convert to the moles, and then if I know the molecular weight, I can then figure out the mass of it. So how do you figure out the molecular weight? Well, you look in the periodic table, and under nitrogen, it's 14.01, and oxygen is 16. And there's 1 nitrogen and 2 oxygen, so 14.01 times 2 times 16 for the oxygen, and we get 46.01 grams for the molecular weight of nitrogen dioxide. So now this is a solution. We have the number of molecules of nitrogen dioxide, then we convert to moles, and then we multiply by the molecular weight. Looking at the units, they all cancel, and then we're left with 365 grams of nitrogen dioxide. And we will talk about ratios of elements and compounds, but let's talk about something colloquially first, like a clover. Clovers typically have 3 leaves. I mean, I know there's other types of, there's 4-leaf clovers, and sometimes you can rip 1 or 2 of the leaves off to have a different number, but generally speaking, clovers have 3 leaves. So how many leaves are on 14 clovers? Well, the same unit analysis works. 14 clovers times 3 leaves to clover, we're left with 42 leaves. So let's look at carbon tetrachloride. So for every 1 mole of carbon tetrachloride, it means that there's 4 moles of chlorine. So just like the leaves on the clover, we have each atom, each unit, each mole of carbon tetrachloride is going to have 4 times as much chlorine. And it works for other elements too. It's a 1-to-1 ratio for carbon, but it's a 1-to-4 ratio for chlorine. So it really just depends on what you're looking for. And this works for other molecules too. So for carbon dioxide, there's 2 oxygen atoms per carbon dioxide molecule, and that also means there's 2 dozen oxygen atoms to 2 dozen carbon dioxide molecules, and then it also means there's 2 moles oxygen per 1 mole of carbon dioxide. So this works out, and you can see that based off of the 2 subscript, and from that you get the atomic ratios, and the atomic ratios carry over to molar ratios. And other colloquial examples, 8 legs to a spider, 4 legs to a chair, and then, the chemistry example, we have 2 hydrogens per water molecule. So let's convert between moles of a compound, moles of constituent element. So how many moles of oxygen are in 1.7 moles of calcium carbonate? So we're given the number of moles of calcium carbonate. We only need to figure out how many moles of oxygen. And this one's a single step, because if you look at the moles of calcium carbonate, there's going to be 3 moles, because each unit of calcium carbonate has 1 mole calcium, 1 mole carbon, 3 moles oxygen. And it works for other units too. It can be dozen, it could be Googleplexes, but we like moles here in chemistry. So let's do the 3-to-1 molar ratio, and then do the math. 1.7 moles of calcium carbonate, but there's 3 moles oxygen per mole of calcium carbonate. Now we get 5.1 moles of oxygen. So you can see here with the dimensional analysis, you can get other information, and then you can also see where the units go and make sure that your units cancel and it works properly. And if you get the end and the units that you want, you're probably doing it in the correct fashion. So find the mass of sodium and 15 grams of sodium chloride. Well, let's see here. Sodium chloride's molecular weight is 58.44, and I'll show you how to. Well, it's the mass of sodium plus the mass of chlorine in the periodic table, and you can see here then the middle step, the mole of sodium per mole of sodium chloride. This is the ratio. And at the end, you already know the mass per mole. That's something that you've been dividing it, but now you can multiply it too. So just make sure that you have the units all work out. So let's look at here. We started with 15 grams sodium chloride, and now we convert this to moles of sodium chloride. Then we look at there's 1 mole of sodium per mole of sodium chloride, and then there's 22.99 grams of sodium per mole of sodium. You can see each unit cancels, and it looks a little weird here because, I guess that's all correct. You're going left to right. And then you're left with 5.9 grams of sodium. Let's talk about other things we can do. We can do mass percents. So mass percent composition is just the mass of whatever's in a compound divided by the total mass of the compound times 100%. And maybe you've done this with body, like what is your body fat percentage? Well, it's the amount of fat that you have in your body divided by the total mass of your body. That's what your body fat percentage is. What is the sodium percentage in a compound? Well, it's the mass of sodium in the compound divided by the total mass of the compound times 100% for that, to get that fraction. And then the 100% just, moves the decimal place over by 2, because we like percents for some reason rather than fractions. So let's look at this. A 0.358 grams of chromium reacts with oxygen to form 0.523 grams of the metal oxide. What's the mass percent of chromium in that? Well, it's the mass of chromium over the total metal oxide. So we know that there's 0.358 grams of chromium, and then it reacts, and then now take the total mass of the metal oxide. We know that mass, times that by 100%, and we get 68.5%. So we can use percent composition as conversion factors. So for instance, the percent composition of sodium and sodium chloride is 39%. And you can figure this out from NaCl. So you would take sodium Na divided by the total mass of NaCl, and then from that you can get 39% that way. So you can write it in a couple forms. So you can, and the idea though is that these are the same units, that you're getting this information, and you can use this information as far as doing dimensional analysis. And you can do the same thing for moles of chlorine, but of course the number would be different. It would be 61 grams of chlorine over 100 grams of sodium chloride, for instance, for chlorine. So let's use the example in the beginning of the class. The FDA recommends adults consume less than 2.3 grams of sodium per day. How many grams of sodium chloride can you consume and still be within the guidelines? Well, we know this. We know 2.3 grams sodium. It's either given to us or we could figure it out. You should be able to figure this out by yourself right now. And then we are going to move from mass of sodium then to mass of sodium chloride. And this way, actually, when we do the math, we're going to have the mass of sodium chloride on the top. And how do you figure this out? Well, because of the dimensions, you want to be able to cancel out the grams of sodium, and you want grams of sodium chloride at the end. And then from this, you get 5.9 grams of sodium chloride is how much the maximum you can have per day under the Food and Drug Administration guidelines for the average adult. So likewise, we can look at percentage of other things and other compounds. This is known as a chlorofluorocarbon. It's a molecule that has chlorine, fluorine, and carbon only. And this chlorofluorocarbon has 1 carbon, 2 chlorines, 2 fluorines, CCl2F2. So dichloromethane. So this here, and what is the mass percent of chlorine in this? Well, it's the total mass of chlorine over the entire molar mass of dichloromethane. And so then you can do the math. Okay, well, I guess we're not going to do that. We're going to look at a different one. So similar problem, but 2 carbons, 4 chlorines, 2 fluorines. We want the mass percentage of chlorine in this. So this one, though, the subscript tells us there's 4 atoms of chlorine for each of these. So we have to do 4 times the mass of chlorine in this divided by the molar mass of the entire molecule. So 4 times the mass of Cl, and we look at this from the periodic table, the 35.45. Then the total mass is 2 times carbon, which is 12.01, 4 times 35.45, and then 2 times 19 for fluorine. And you do all that, you get 141.8 over 203.8, and then that comes down to 69.58% chlorine. So from this, and using the periodic table, you can come up with the mass percent of chlorine in this molecule. So other things that we can use this for, so fluoridation in drinking water. Different places don't necessarily have fluorine in it. Hawaii doesn't have fluorine in the drinking water. And we also have a very high incidence of cavities in the state. Much of the well water. This was actually discovered in Colorado, that there was high fluorine in the water, and one of the dentists noticed that no one really had cavities, and so they figured out that, that there must be something going on here, that there's something in the water that's keeping people from their teeth decaying. But there can be an issue with this if there's too much fluorine and the teeth become brown and spotted. This is called dental fluorosis, and very high levels can lead to skeletal fluorosis because the mineral that's at that's your tooth enamel, it's called hydroxyapatite. And what fluorine does is it replaces the hydroxide in the mineral, and it makes the mineral stronger, and it also makes it less soluble. So also fluorine inhibits the growth of bacteria in general. So all these conditions make fluorine very good for your teeth and for your oral health. But of course, like many moderation things, you can have too much. And the healthiest is about 1 to 4 milligrams a day for adults. So, but too much can cause fluorosis. So depending on the adult, but if you drink between 1 and 2 liters of water per day, I want to know what the beneficial amounts of fluoride from the water. It's often used sodium fluoride. So, well, first of all, what is the mass percent of fluoride and sodium fluoride, and how many grams of sodium fluoride should be added to 1,500 liters of water to fluoridate it to the level of 0.7 milligrams fluoride per liter. So everything you've learned so far, you should be able to that. So if you were a chemist working in the waterworks and your boss gave you this problem, you have enough tools that you can do this. So let's talk about empirical formulas. Empirical formulas give you the smallest whole number ratio of each type of atom in a compound, but not necessarily, it could be, but not necessarily the specific number of each. It could be, but it's the smallest ratio. And the molecular formula is always a whole number of the empirical formula. And that could be 1, but it could be more. It depends on the compound. So for instance, the molecular formula for hydrogen peroxide is H2O2, but the empirical formula is just HO, 1H1O. And the molecular formula is just the empirical number times 2 then for hydrogen peroxide. And atoms only work for whole numbers. So when you deal with atoms, you deal with what is known as discrete mathematics. It is not continuous mathematics where there is an infinite number of points between 2 points where you can divide down, but for atoms you deal with discrete mathematics, which means whole numbers only. So keep that in mind when you do chemistry, is discrete math. So let's do some more. So we're taking a sample of water and it decomposes and we get 3 grams of hydrogen gas and 24 grams of oxygen. What is the empirical formula from these data? So how are we going to figure this out? Well, the first thing, of course, is in chemistry we think of moles. So convert the mass to moles. 3 grams of hydrogen is 3 moles of hydrogen, and 24 grams of oxygen is 1.5 moles of oxygen. So that means there's 3 moles of hydrogen for every 1.5 mole of oxygen, but those are not whole numbers. So we cannot write this. We can't say H3 oxygen 1.5 and be done. No, we have to divide by the lowest number there, and we get H2O. And you have to keep on doing this until the fraction goes away. So keep that in mind. You have to, if you get a fractional value, you have to go until the fractions go away. And the empirical formula of water is actually having the molecular formula of water is 2 hydrogens to 1 oxygen, H2O. So how do we do this? Right, so to get the empirical formula from experimental data, first of all, get the masses of each. If it's percent calculation, if you write out given the mass, you can go there. If it's percent, just assume 100 grams and then just get the masses from each step. Convert the masses to moles and then divide, right? You can write a pseudo formula if you want. I usually just go and divide the number and then keep on working until you get all whole numbers. So, okay, so let's do an example of this. Something is 60% carbon, 4.48% hydrogen, and 35.53% oxygen. Find the empirical formula. So 100 grams sample, so 60 grams carbon, 4.48 grams hydrogen, 35.53 grams oxygen. So to do this, you can do this on your own. Same step. You get the moles, get the lowest number of moles, then divide that commonly through, and then work until you can get rid of the fractional parts to get the whole numbers. So let's look at another one. 3.24 grams of titanium reacts with reacts with oxygen to form 5.4 grams of a metal oxide. What is the empirical formula of the metal oxide? So 3.24 grams titanium, 5.4 grams metal oxide. Well, what about the mass of oxygen? Well, we can use the missing mass. So we can use the missing mass, and so the mass of oxygen is just the mass of the oxide minus the mass of titanium, so we get 2.16 grams of oxygen. Now we can convert it to moles. So, and then use the same step there. So we're trying to get you to think and build up. And actually oxygen, we didn't know what oxygen was for a bit. Oxygen was kind of mysterious. And so we were wondering, why do metals tarnish? And there was also some extra missing mass in certain compounds. And it has to do a lot with combustion analysis. We would burn things, and then we would, and this is a lot of what Lavoisier did, this was like, all right, well, we know how much it started, we burned it, and then we're kind of missing some mass here. And the idea of the element oxygen was then, there's this missing mass here, and this is probably an element. And it turned out the element is what we know as oxygen. Good old oxygen. So let's look at some other things from the molecular formula. So the molecular formula is always a whole number multiple of the empirical formula. And so we just have to multiply it by the number there. So for instance, if the molecular formula is carbon, 2 hydrogens to some oxygen times some multiplier, and then we just have to figure out what that multiplier is. So for instance, fructose has an empirical formula of C2H0, and its molar mass is 180 grams per mole. What is a molecular formula then for fructose? And so if we count up the molecular mass or the molar mass of the empirical formula, it's 30.03, and it was given that it was 180 grams per mole fructose. So 180 divided by 30, that's 6. So that means there's 6 units of this empirical formula. So we take the formula C2H0, multiply it by a factor of 6, and we get C6H12O6. And you can also see, I mentioned this in a previous chapter, that's another way you can see you get the word carbohydrate, where you have carbon times with water, CH2O, the carbohydrate. So that's where if you ever wondered the root of the term carbohydrate, now you know, it's from chemistry class. So these are the steps then, how you go through and review. So some review of this, we learned about the mole. The mole is Avogadro's number of something, and it's very convenient to use Avogadro's number because atoms are so huge and we just can't physically count them all, and this makes it a lot easier. And we've learned about the mass equivalent of the atomic mass and the mass formula, and also the mass of 1 mole of an element. And we can use the molar ratios, I guess going back to chemical formulas, we can tell each kind of element, and then we can get ratios, and then we can extract all sorts of information from this. And we can also work with relative masses and compounds, and we can also use information of this kind and the skills today to figure out the empirical formula, and we can also form this molecular formula if we have other information. Here are the learning objectives and the disclaimer. Thank you for listening.